Hello. Today we're going to be talking about Chapter 4, Section 1, which has to do with antiderivatives and indefinite integration. So first we need to know what an antiderivative is. Suppose you were asked to find a function big F whose derivative is little f of x is equal to 3x squared. Now, using derivatives, you can say that big F of x is equal to x cubed, right? So here we have big F of x equal to x cubed, and you can see that because if you took the derivative of big F, you would go back to 3x squared. Now, this means that the function big F is an antiderivative of little f. All right, now you'll notice I said the function big F was an antiderivative for little f, meaning that there can be multiple antiderivatives for one function. For example, here I have big F sub 1 of x is equal to x cubed, and big F sub 2 of x is equal to x cubed minus 5. So if you took the derivative of both of these functions, you would get the same function, 3x squared, here. Now this is because when you take the derivative, the any constant that you have in the function becomes 0, right? So it doesn't matter. This means that for any constant c, the function given by big F equals x cubed plus c will be an antiderivative of f, no matter what value c is. And this brings us to theorem 4.1, which basically states that if big F is an antiderivative of little f on a certain interval, then g is also an antiderivative of little f as long as g of x is equal to big F of x plus c. Now to prove this, let's just say that big G of x is equal to big F of x plus c, and that big F prime is equal to little f of x. Now, if we were to differentiate g, we would get big G prime is equal to little f of x, because when you differentiate big F, you'll get little f, and then when you differentiate c, it'll become 0. All right. Now let's go over how to solve a differential equation using antiderivatives. So say you have the differential equation dy dx is equal to little f of x. Now, in order to solve for y, we first need to separate the variables. And in order to do this, we can just move dx to the other side so that we have all the x's on one side and y on the other. Now, in order to solve for y, we need to use antiderivatives. So this symbol right here is called it's an indefinite integral, and it's basically synonymous with an antiderivative. And so when you do this, when you integrate dy, you'll just get y, and then when you integrate little f, you will then get big F of x plus c. Now it's important to remember the plus c, because for every function there are many antiderivatives, and so this constant of integration is really important.
All right, so we already know what differentiation is. Let's run a quick example of that. For example, y equals 2x. If we take the derivative of that, we know that dy dx equals 2. That's pretty straightforward. We know that it's the instantaneous slope, and in this example, because it was linear, it's just going to be a regular number. But now I want to get into something about integration, the relationship between differentiation and integration. If we were to look at the example we looked at earlier of y equals 2x, and we were to graphically model it like this, and we say this is y equals 2x, we know that the slope or the derivative of this graph would be 2. So then if we were to then create a graph modeling that derivative, we would get something like that. If this is 2 right here, this is y equals 2. Right, so the derivative of this, of this graph would then produce something like that. Good. Because the slope at any given moment in time of this graph is 2, we know that this function will always be 2. Now, what about if we want to get back here? We're already familiar with integration, but this should help you guys really understand what it really means graphically. Let's look at how this function, the one right here, correlates to the one right here. At every given moment in time, we can see that the area right here is increasing at a steady rate, right? Because this function is straight. You know, if the area was going like this or was curved, then we know that the area would be changing at a different rate. But the area is growing at a constant rate. That constant rate is similar to the slope right here, the slope of 2. And in fact, the slope, the area, is at every increment of 1 is getting bigger by 2, which would be the original function right here. So in order to get from here to here, we would integrate or calculate the area underneath the curve or line between this function, right? The graph, the axes, and then the line of the graph. So if we were to then take the integral, right, of our function 2 dx, we would then get 2x. Alrighty. So let's get into the biggest rule of integration, the most basic rule of integration, which is the power rule, which is we're already familiar with the power rule for differentiation. Let's quickly run through that. For example, as a review, if we have y equals x cubed, we know that we would take this number, bring it down, and as a consequence of doing that, we would then subtract 1 from the number up there, which would then give us something like 3x squared. That would be the derivative of y, dy dx. And we know that. Now, let's say we want to integrate, and we discussed earlier in the previous video that integration is the opposite of differentiation. So in theory, if we took the derivative of this y equals x cubed, and then we were to, and then we get this, in theory, we should be able to get back here by integrating. So let's do that. We already know that the integral of 3x squared dx is x cubed because we see in the example. But let's actually run through the rule. The rule that we used to get here was the power rule for differentiation. So now let's cover the power rule for integration. The first thing we're going to do is the opposite. So if we start with our good 3x squared, we're going to want to add 1 to the exponent right there. Now, we take the new number right here, 2 plus 1 is 3, and we're going to divide the whole number by 3, which would affect this constant right there. Now, 3 divided by 3 is going to be just 1, giving us x, and of course 2 plus 1, like I said earlier, is 3. Notice how we got exactly back to the original. So that's the rule. It's the opposite. So let's run through maybe a few more examples. Let's say we have the y equals x to the 4th. If we were to take the integral of that, remember we add 1 right there. That's 5, and then we would have to divide by that new number. So that would give us x to the 5th times 1/5 right there. Let's do one final one. Let's say we have y equals 6x to the 4th. All right. If we were to integrate that, if we were to integrate this, we would get, remember we have to add 1 to the top, so we would get x to the 5th. It's easiest to do the exponent first, and then we would divide by that new number right here, so we would get 6 over 5. So that's it, power rule for integration. Quick rundown. Again, it's if we have n right here, we would do plus 1 right there, and then divide by that new number. All right.
Alright, we're going to start with our first example here today, which is going to be turning this left antiderivative into the derivative on the right. And the first step that we want to do here is we want to expand the left integral so that we divide the x into the 3/2 into the x squared minus 1. And when we do that, we get the integral of x to the 1/2 minus x to the negative 3/2 dx. Make sure you include the dx as without that, you will not be able to integrate and get a plus c, which is a constant of integration. And then what we want to do is we want to use a sum rule, which is where we see that since there's a minus sign right here, we can actually split up this whole integral into 2 different integrals. And when we do that, we get the integral of x to the 1/2 dx minus the integral of x to the negative 3/2 dx. And after that, what we want to do is we want to actually integrate and then use the reverse power rule where we add 1 to the exponent and then divide by the reciprocal. So when we do that, we get 2/3 x to the 3/2 plus 2x to the negative 1/2 plus c. Make sure you include this plus c because that signifies the constant of integration, which is because this is we're doing a indefinite integral, we will always have a constant of integration since there are no limits. And when we do that, as you can see, this form does not really represent the form that the equation wants us to make it into. And to get it into that form, what we want to do is we want to multiply by negative 1/2 to both sides and divide by 3 on both sides. When we do that and combine the sum, we get 2 times parentheses x squared plus 3 divided by 3 root x plus c. Here we have our second example where we're given an antiderivative and told to find the indefinite integral and check the result by differentiation. So first what we want to do is, as we did in the previous example, expand the integral so that we have so when we have x plus 1 times 3x minus 2, we get a polynomial, and that equals 3x squared plus x minus 2. So next what we want to do is, since we know these are all polynomials, we can do the reverse power rule, and when we do that, we get x cubed plus 1/2 x squared minus 2x plus c. Remember that we need a plus c here because this is an indefinite integral, so we need a constant of integration. Next, since it wants us to check the results, what we want to do is actually differentiate our solution right here. And when we do that, we get 3x squared plus x minus 2, which you can see in our expanded equation right here that they're the same. So that means that our result is correct. So now for our third example, we're going to visit a very similar problem to the last one, but with a few changed details. So this problem requires us to find the indefinite integral and check the result by differentiation. Same as the last one, right? But what's different about this one is that we actually have trig functions, which if you remember early in the chapter, we learned about how to solve trig functions with integrals. And what if you remember, they're actually just the inverse formulas of the derivative trig function formulas. So what you can do is, when you're trying to solve these problems, you want to assemble the trig functions in a way in which you can use these formulas to your advantage and actually solve the integral. So right here we see secant x times the tangent x minus secant x in parentheses dx. But these aren't any formulas you can recognize, so usually what we want to do is multiply this equation out and expand it. So when we do that, we will get the integral of secant x tangent x minus secant squared x. And if you guys remember, this is actually 2 of our trig formulas, where secant x times tangent x equals secant x, and then the integral of secant squared x equals tangent x. So when we use these 2 trig formulas, we get secant x minus tangent x plus c, because this is an indefinite integral and there are no limits right here. But it asks us to check the results using differentiation. So what we can do is differentiate secant x minus tangent x plus c. Secant x equals to secant x tangent x, then tangent x equals secant squared x. And remember that the constant, when you differentiate it, will always equal 0, so you do not need to add it. So this problem that we have here is a little bit unique in that it actually requires you to apply integrals. So what we have here is the differential equation f prime of x equals 4x. We are given the particular solution f of 0 equals 6. So as you can see, we have a known solution for f of x, and then we are given f prime of x. So what we want to do here when you're given these types of problems is try to find f of x. And when we do that by integrating f prime of x, because since the integral of f prime of x equals f of x, which will then equal the integral of 4x, which is 2x squared plus c. So when we get that, now we know that our goal in this problem is to try to find the constant, since we are given the solution. So what we want to do is plug in f of 0, which will be 2 times 0 squared plus c equals 6, and now we know c equals 6. So now we know that our equation is f of x equals 2x squared plus 6. Here we have our second example, where we're given an antiderivative and told to find the indefinite integral and check the result by differentiation. So first what we want to do is, as we did in the previous example, expand the integral so that we have, so when we have x plus 1 times 3x minus 2, we get a polynomial, and that equals 3x squared plus x minus 2. So next what we want to do is, since we know these are all polynomials, we can do the reverse power rule, and when we do that, we get x cubed plus 1/2 x squared minus 2x plus c. Remember that we need a plus c here because it's an indefinite integral, so we need a constant of integration. Next, since it wants us to check the results, what we want to do is actually differentiate our solution right here, and when we do that, we get 3x squared plus x minus 2, which you can see in our expanded equation right here that they're the same, so that means that our result is correct.